So I want to talk about a notation that's called sigma notation or summation notation. For those of you following along in the Thomas textbook, this corresponds to section 5.2. I believe that this is something that you would have seen again in an algebra or pre-calculus course, but it comes up again in calculus, and so I want to review it now. What sigma notation does is it allows us to specify the sum of some function of a series of integers in just a convenient way. So here I've written in the first example, this is an example of how we would use the notation. I've written the sum. This is, you pronounce it this way. You say sum from k equals 1 to 5. And the notation is you write this sigma. This is Greek letter capital sigma. And underneath it, you write an index name, which in this case is k. I'll explain in a minute what the difference is between an index and a variable. So this is the index name, which is k. You say equals some number. That's going to be the lowest number that you're going to substitute in for k. And then on the top, you're going to write the highest number that you're going to substitute in for k. And these have to be integers, and unlike most of the things that we've done so far where we're assuming we have intervals of real numbers, k can only be the integers. So it's going to be an integer starting with the number on the bottom and ending with the number on top. So for example, if I write sum from k equals 1 to 5 of k, what that means is that I'm simply going to let k cycle through all the integers from 1 to 5, and every place, and for every integer, I'm just going to replace k with that integer, and I'm going to put a plus sign in between them. So this is 1 because it's k equals 1, it's k equals 2, k equals 3, k equals 4, and k equals 5. In this particular case, the thing that I'm adding up is k itself. That's why you don't see any difference between the k equals 1 here and the blue 1 that you see on top of it. But just as another example, I've written here the sum from k equals 4 to 8 of k cubed. So what I want to do is I know that k is going to be k is going to start at 4, so it's going to be n equals 4, and then I'll write them this way, n equals 5, n equals 6, n equals 7, and n equals 8. I put plus signs in between them. And now, for every one of these terms, since what I've specified is k cubed, I'm going to cube the k value. Sorry, I've written n's here, because I often do this with n's. So let me just switch these to k's quickly. Okay, they should have been k's. Sometimes we do it with n, sometimes we do it with k. So all right, so every place that you see here, every place that you see k equal 4, we're going to replace it with 4 cubed. When we see k equals 5, we're going to replace it with 5 cubed. So this is 4 cubed is 64, and 5 cubed is 125, 6 cubed. So k equals 6 is 216, k equals 7, that's 7 cubed, that gives us 343, and 8 cubed is 512. When we add all of these up, let me just do this quickly in my head, that gives us 1260. I didn't really do that in my head, that was in my notes. So the fact that it equals 1260 is not the important thing. The point is that this is a shorthand for this. It's just a shorter way of saying we're going to add up this function, the cubed function, of all the integers from 4 to 8. So, a slightly more complicated example would be something like this, where the thing that we're going to replace the integers with is a more complicated function. It's sine of 3k plus cosine 4k plus 1. So this is going to be sine of 3 times negative 2 is negative 6 plus cosine of negative 8 plus 1 is negative 7. Don't worry about the fact that we don't really know off the top of our head what the sine of negative 6 radians and cosine of negative 7 radians are. It doesn't matter. I'm just going to zip through the algebra here. So we can see that we have 6 integers between negative 2 and positive 3 that we have to cycle through, and in every case I simply replaced k with whatever k was. Sorry, I wrote these again as n's instead of k's So you can tell I'm very used to doing this with n's, but it doesn't matter whether it's n or k. So every place that I see k, I simply replace it with the appropriate value of k, in this case I simplified it, but that's all we're doing. So this, once again, the point is that this is really a shorthand for all of this that you see here. Now, why is it that I've referred to k as if it's not a variable? After all, aren't all letters variables? This is the mistake I think that many first-year calculus students make, is assuming that anytime that there are two things that something can be, either it's a number or it's a variable, which we represent by a letter, usually a letter in the Roman alphabet, sometimes a letter in the Greek alphabet for reasons just because math professors like to torture people with the Greek alphabet. But the fact is that none of this is true. A variable is the concept of something that could take on any number of values. K isn't really doing that. K is taking on very specific values. It's not like K, like we're saying, K is some unknown in the sigma expression that I'm pointing to. It's not like I'm saying that K is some sort of unknown that could take on values between 10 and 13. Rather, K is a known value. We're specifically assigning it all four values that are 10, 11, 12, and 13, and using them in a specific way. So I can write this expression and I can write this expression, and they mean the exact same thing. This is really just a shorthand for this one. And by the way, so is this. This would be another way to write the exact same thing, where here I've simply used the numbers k equals 1 to 4, but added 9 to each of them, so that in each case I generate 10, 11, 12, and 13 when I replace k with 1, 2, 3, and 4. So that's not true, for example, for the expression, let's say f of x equals x squared. Here I'm talking about a function that really could take on any value like that. I'm not assigning it specific values. I'm really using this to represent the idea that I don't know what x is and could actually assign it anything. So it's important to understand that this is a distinction. The k, or what I've been calling n, is not a variable. It's just an index, and it's just sort of a convenience. Those of you who've programmed computer before, I know that there are a number of computer science or pre-computer science majors in this class. Essentially what this is doing is taking on the role of the index in a for loop. Like, I'll just write this in very simple high-level basic. If I write, for I equals 1 to 4, print I, and then print the character plus. What this would do is it would let I cycle through 1 to 4, and then the first thing you do is you'd print the number 1, then you'd print a plus, then we go around again and set I to the next value. So then we go through these instructions again, print 2, and then print a plus, and we keep going. So that's really more what the sigma does. And by the way, for those of you who don't know anything about computer programming or are not computer science majors, don't worry about you can just ignore like the last 60 seconds of what I said. You don't need to know that to do calculus. I'm just trying to demonstrate to those who find this analogy useful that this is really what the sigma is doing. It's really just kind of almost like a pump that allows us to pump out a sum with lots and lots of numbers that are being added up.